MO theory as it applies to resonance. So we got to this depiction of a pi bond. Not your normal depiction of a pi bond. It's not just two p orbitals side to side. It's actually now 3 orbitals side to side to side. But if 2 orbitals can overlap and create a new molecular orbital, then why can't 3 orbitals overlap and make a new molecular orbital? I mean, it's called a molecular orbital because it spans a molecule, right? Why would it need to be limited to spanning just 2 atoms if it can span 3 or 4 atoms? So we got this system, and then we said that just above this is another molecular orbital that is out of phase, and then a last molecular orbital that is completely out of phase. And what did we call these regions where the orbitals change phase? These are nodes, and the nodes increase with increasing orbitals. That's actually not new. The first energy shell, the 1s orbital, 0 nodes. The second energy shell, all orbitals have 1 node. They're higher energy, they have a larger number of nodes. Third energy shell, 2 nodes. Fourth energy shell. Every time you go up in energy, nodes are created. Do you remember the other interesting property of this? We were looking at this 3-atom system with a positive charge, and we said the nuclei fall in the middle of these orbitals, and that center atom is skipped by this middle orbital. The orbital doesn't show up there. And I don't know if this feels weird to you or not. Remember, orbitals describe where electrons are and how they behave. And we're saying that there can be electrons here that show up on one side or the other of this central carbon, but not in the middle. You know, like, I don't live here, I work here, but I live over in Mill Creek. Imagine if I didn't have to go between Taylorsville and Mill Creek, but I could just be in one place or the other. That's what this electron is able to do. That might feel weird, but it's totally normal. If we were to describe that as a wave in the ocean, it might look like a wave that has this plateau. There's no wave there. But for whatever reason, the wave is rising in one place, falling in another. It's similar to that. I think we also looked at this and we said that there are 2 pi electrons in this system. There's a lot of sigma bonds, but there's only 1 pi bond, and those 2 pi electrons are going to fall into the lowest energy. So MO theory says there is a pi bond across all 3 atoms. Lewis structure makes it look like there's a pi bond just on the left. Or if I move the electrons from the left to the right, remember these electron arrows say, I'm talking about these electrons, and I want to show what happens when these electrons are over here. Then our resonance form showed the pi bond on the right and the positive charge on the left. But MO theory says it's not either of those. MO theory says it's not a pi bond on the left, it's not a pi bond on the right. It's a pi bond across all 3 of them. The resonance hybrid shows this partial double bond character with this delocalized positive charge.
Is that because it always exists in that state, or is it because it's moving so quickly it's the same as...
Right. Good question. Is it always in this state, or is it just moving so quickly between these? Do you guys remember the definition that I gave for resonance yesterday?
Vibration.
Well, we gave this analogy of vibration, but I wrote out a definition on the board, a short one. Good. Movement / delocalization of pi electrons. This looks like movement. And so your question, Michael, of is it just moving so fast that we can't really tell the difference? No. Lewis structure makes it look like the pi electrons are moving from one side to the other. MO theory tells us it's not movement. It's a pi bond that spans 3 atoms. Until now, you probably have not seen this. That's my suspicion. You've not seen a pi bond that spans 3 atoms. Why would you? We told you that bonding happens between 2 atoms. But MO theory is telling us bonding can happen across a molecule. If bonding is just this overlap of orbitals that creates new orbitals, then this is a bonding of 3 orbitals across 3 atoms. So it's not movement like Lewis structure would have us believe. It's delocalization. The pi bond is not localized here. The pi bond is not localized here. The pi bond is delocalized across this 3-atom system. Isn't that amazing? It is. It's all that quantum theory. Now, this next orbital is empty. There's no electrons in it. So we can think of that as a positive charge, a lack of electrons. And where would that vacancy of electrons show up? It shows up on the left carbon and on the right carbon, but not in the middle. It shows up on the left carbon or the right carbon, but not in the middle. This next molecular orbital tells us exactly where that positive charge goes. And if you'll bear with my weird color combinations, if I were to put 1 electron there, this is a radical species, has an unpaired electron. That radical species can be shown in resonance as well, which means really it behaves more like this partial double bond with a radical. And if I put another electron in here, then I have a lone pair on a carbon and a negative charge. And that lone pair and negative charge is not on one spot, but it's delocalized across those 2 carbons. The resonance hybrid doesn't do a perfect job of explaining what MO theory does. The resonance hybrid does a better job of explaining MO theory's perspective. But wouldn't you agree that the resonance hybrid, it kind of makes it look like the negative charge, the radical, and the positive charge are on all 3 carbons? There's no way to pin down where that charge or where those electrons are. But MO theory says the positive, the negative, the radical are not on all 3. They're either here or in Mill Creek. They're not in between. They're either on the outside carbons, but they're never found on that center carbon. That's what MO theory tells us. I have very few test questions on MO theory because I find them challenging to write. But if you want to understand organic chemistry, you've got to grasp at least a little bit what molecular orbital theory tells us. Because I can show you resonance with Lewis structures, and you could believe them. But they're a lie. They're a simplification. MO theory, on the other hand, just is too constrained. I can't show the rest of the molecule. I can only show this like specific snapshot of some bonding. All right. So why don't we, we talked about the 2-atom system and the 3-atom system, right?
We're at arrow pushing.
Good. You're welcome. So why don't we take the, I guess I'll just kind of skip this, but these 2 resonance forms on the right are the resonance forms that we look at down below. I guess we also have that bottom left one as well. Why don't we look at what arrow pushing is necessary to interconvert those Lewis structures to show the behavior of those. So I've got this 6-membered ring fused with a 5-membered ring, and I've got 2 nitrogens. As we look at the other resonance form, we see that the double bond has shifted and we've created charge. A positive charge on one nitrogen, a negative charge on the other. Can you propose electron arrows that allow this? Propose electron arrows on the left that would show how this forms on the right. Yeah, draw arrows on this left structure that demonstrate how that right-hand structure forms. Essentially, show the movement that describes the relationship of the resonance. Without going through to look, I want to guess at what some of you have done. I imagine that some of you have noticed a lone pair on this nitrogen on the top ends up on this nitrogen on the bottom. I go from 1 lone pair and 1 lone pair to 0 lone pairs and 2 lone pairs. So I would wager that at least one of you has drawn an arrow that says this lone pair, don't copy this down, this lone pair goes to this nitrogen. You're looking at how the electrons are moving and you're saying, I need to get an extra lone pair down there. And probably those same people would say this pi bond ends up in a different place. So here is my pi bond moving. The problem in what you've suggested is that one nitrogen that is in this 3-atom system has just lobbed its electrons away. And it really is not able to do that. That lone pair is able to be shared with the atoms adjacent to it or kept, but it cannot be tossed completely. Also, you're saying that these electrons shared between carbon and nitrogen are taken by the by the carbon to be shared with the other nitrogen. But in a bond between carbon and nitrogen, nitrogen owns the electrons. Nitrogen is more electronegative. So if these electrons are going to move, they're nitrogens to move. Here's how I have found that you can summarize electron arrow pushing 95% of the time. When a bond forms, it forms with electrons from the more electronegative atom. So instead of saying that the pi bond between N and carbon formed because the pi bond shifted up that way, I'm going to say that this pi bond forms from the more electronegative atom's electrons. Nitrogen is deciding to share its electrons. Nitrogen forms a pi bond. When a bond breaks toward the more electronegative atom. When this carbon-nitrogen bond breaks, it is nitrogen that gets to reclaim the electrons. So I show that bond breaking toward the nitrogen. With that in mind, I would like you to draw the one underneath with the OH group. Show arrows on that first structure as needed to make the structure on the right. Sorry, was I right? Did anybody do what I said the first time? The lone pair moved over? Yeah? It's an intuitive idea. Where is the lone pair going? Where is the pi bond going? But instead, I want you to think about how far can these electrons move? These electrons cannot move very far.
Like only as far as they're touching
Pretty much, yeah. Only as far as they're touching. Or staying with something that they're touching. Yeah. Does anyone feel brave enough to describe the arrows they drew? Rowan?
I drew the lone pair from the oxygen going over like one bond, and then the double bond going over to the positive.
Good. I could draw that arrow going to the positive. I could show that arrow going to the bonding region. Either one of them would be fine. So Gavin asked, electrons can only move as far as they're touching. Well, these pi electrons are touching these two carbons. And so these pi electrons are able to move somewhere in the vicinity of these two carbons. So we're saying that this carbon on the bottom is taking the pi electrons and just shifting them over to the other side. So it's moving as far as it's touching. It's not moving any further. And oxygen is taking one of its two lone pairs, and it's dedicating that lone pair to make a second bond with the carbon that it's attached to. What did I forget on the right? Forgot my charge. Positive charge on a 3-bonded oxygen.
Why does that second bond even happen in the first place?
Good question. I have a hydrogen on this carbon. So if I show a resonance form that takes a lone pair and makes a double bond without moving the other double bond, too many electrons. I've broken my octet. So I think you'll notice that this arrow actually doesn't follow my two rules, because I'm not breaking from a more electronegative atom or to a more electronegative atom. It's all carbons. But this arrow forces the necessity of this bond breaking, and this bond breaking has only one place to go, to a vacant spot, to a spot that has room for more electrons. Not all resonance forms are equal to each other. Resonance contribution follows 3 rules. Not all of the rules that we tell you in chemistry go in order. These 3 do. If you do not follow these 3 rules in order, you can't make predictions about resonance forms. Rule number 1, we want to minimize charges. This is something I like to teach in general chemistry because not all textbooks teach it this way. When I see students drawing boron trifluoride, I see them aiming to make an octet everywhere. So they give a double bond with fluorine and boron, and they say, that's good, my boron now has a full octet. These are resonance forms. No sigma bonds change. It's only the location of pi electrons across a 2-atom system. What they don't teach in most textbooks early enough is that this fluorine takes on a positive charge and boron a negative. So by giving boron an octet, we have created 2 charges unnecessarily. So we say that this is not the major form of boron trifluoride because it has maximum octets. This is what the molecule looks like. This is a major contributor. We also say that this is more stable. It behaves more like what the molecule really behaves like.
And the way we could determine if like an atom is an exception to the octet rule is if we draw all our normal charges, and we want to have the smallest charge.
Actually, every single time you have an exception to the octet rule, whether it's electron deficient or hypervalent, something that takes on more than 8 electrons, it's always charge. When you look at sulfur, sulfur can make up to 6 bonds. It can have up to 12 electrons around it. And it does that in order to minimize its formal charge. It's always in the game of formal charge.
So why do we even state the octet rule? Just because it's generally correct?
It's generally not correct, to be honest. Hydrogen doesn't follow the octet rule. Sulfur and phosphorus and most of the halogens don't follow the octet rule all the time. Even xenon, which is a noble gas and should be inert, can break the octet rule. The octet rule only applies to carbon, nitrogen, oxygen, and fluorine. And I guess because those 4 are common enough elements, it's a good rule to keep in mind. Again, here cannot break the octet rule, regardless of how you care about formal charges. But actually, with that in mind, this structure wasn't even complete. That oxygen now has a positive charge, and technically that carbon has a negative, because resonance forms have to have the same charge. So I want you to look at these 2 structures up here that we just drew arrows on. Which of them is a major contributor to the molecule?
The first one?
Structure on the left. Why? No charges. Major contributor. Rule number 2. We aim to maximize octets. Oh, do you see why this rule has to come after minimum formal charges? If I first tried to maximize octets, then I would say this is a better form of BF3. But we already have a rule established. Don't do octets if it means you're going to create unnecessary charges. First, minimize charge, even if that's at the expense of octets. Then maximize octets. Okay, so we had this structure that we drew yesterday, the one that was up above. And we had 3 resonance forms. One of them was shown up above. The other 2 are then shown down below. And I did have you guys skip over drawing these arrows, but we're actually going to come back to this as well. And we said here, we want to maximize octets. How many of those resonance forms maximize octets? Do any of them lack any octets?
Do lone pairs count for an octet?
Lone pairs definitely count towards octets.
I don't think so.
Which one?
The furthest to the first one,
This lacks an octet. Where?
nitrogen only has 7, should have 8.
Nitrogen? Nitrogen has a lone pair. 2, 4, 6, 8. So nitrogen's got an octet.
It would be, I want to say it's the one in the middle. Nitrogen.
Nitrogen here has 2, 4, 6, 8. Nitrogen's got an octet. I've added the lone pairs in case that helps. The last one who lacks an octet, where?
It doesn't have an octet missing. It's got the 2 bonds inside the hydrogen.
2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So none of them lack an octet. Wrong. Carbon lacks an octet when it has a positive charge. The first structure lacks an octet. All of the other atoms almost always have an octet, whether they have a charge or not. They always have an octet. It's carbon that typically lacks an octet So another way that we can say maximize octets, we could say maximize bonds to carbon or give carbon 4 bonds. That's really what we're saying. Oxygen had an octet the whole time. Nitrogen had an octet the whole time. But by sharing their electrons with carbon, that was the only way carbon could get an octet. So this form on the left, we call this the minor contributor. This is not what the molecule looks like very much. It's the worst resonance form. They all have the same amount of charge, but this one lacks octets. Our third rule, and I'm thinking to put the third rule underneath that one because that structure is going to do really well for the third rule. Yeah, I think I will just put it. Well, I want you to be able to read it. So I'm coming back to this one. The third rule is appropriate charge placement. In these three forms, I place a positive charge on carbon, nitrogen, and oxygen, atoms with very different electronegativities. When carbon holds the positive charge, that would be the best charge placement because carbon is the least electronegative. But it breaks the octet. It doesn't give it an octet. So not a good placement because it breaks rule number 2. Between nitrogen and oxygen, where is a more appropriate place for that positive charge to be? Nitrogen, less electronegative. If we were dealing with a negative charge, we would say, put it on oxygen. So we base appropriate charge placement based on what the charge is, positive or negative, and the electronegativity given that octets are filled. So what is the major resonance form of this structure? The one where nitrogen holds the positive charge. So now I want you guys to do this oxygen-containing structure again. And I want you guys to tell me which of these is the major resonance form. Take 20 seconds, think about it. Take 20 seconds, debate about it amongst the people around you. It should feel, if it feels counterintuitive, that means that you have already established some chemical intuition. You know what feels right about charge, you know what feels wrong. You gotta fight that chemical intuition. Follow the rules. But it's okay to have chemical intuition. Patrick? Oh, I thought you were gonna add something. Okay, which of these is the major resonance contributor? Why? Good. Rule number 2, it maximizes octets. Because both forms have the same amount of charge, we look to maximize octets, or in other words, give carbon 4 bonds. By the way, carbon has an octet if it has a negative charge. It has an octet with a negative charge. So technically, a negatively charged carbon in an environment like this would maximize octets. Even still, you want to give carbon 4 bonds because carbon with a negative charge is not an appropriate charge placement if that charge could be on O or N.
carbon had a negative charge, so technically you check the box 2.
Yep.
But then when you move on to 3, that's not appropriate. So
Correct.
then you move it.
Correct. If carbon has a negative charge, technically 2 is good. But if you can place it somewhere better, like nitrogen or oxygen, and this is what Michael was saying, this feels counterintuitive because why is it better to put a positive charge on oxygen? That's not appropriate charge placement. You're right, it's not. We're not following rule 3. We're following rule 2, which is higher priority than rule 3. Michael?
So I was going to say with carbon that it's better to have carbon bonded to something else than have some lone pairs.
Yeah. If possible, it's better to have carbon bonded to something else. Carbon with a lone pair loves to share that lone pair. So if it cannot have that lone pair, it's more stable.
Why is it that way? Because isn't oxygen more electronegative, so wouldn't it have preference to have more electrons?
Yeah.
So why would it
Well,
stay more positive?
oxygen has the same number of electrons.
Oh,
I mean, it still has an octet, is what I mean. Has 8 electrons, has 8 electrons. So why is it that oxygen prefers to share more? It's not really just about oxygen, it's about the molecule. And remember, this molecule, well, this one's a little bit more complicated because it's a 1, 2, 3, 4 atom system rather than just a 3 atom system. But the molecular orbital diagram of this would say that positive charge is not just on oxygen. There's actually a resonance form we didn't draw here. There's this resonance form as well. Look at this 3-atom system, 1, 2, 3. It has a pi bond and a charge. And I can move the electrons towards the vacancy in that positive charge. And I get that rearrangement of pi electrons and positive charge. So that's a 3-atom system. And then this is a 2-atom system. I have a lone pair right next to a positive charge. And that allows me to get to this resonance form. But molecular orbital theory says that positive charge is on all 3 of these atoms. That positive charge is not in one place. There's a molecular orbital that would sit on those 3 atoms. And that molecular orbital is empty. So, empty pi orbital, empty pi molecular orbital. All right, we got a lot to move on to. We're going to talk about resonance more, but the next thing to talk about is acids and bases. And the first type, a review for us, is Bronsted-Lowry acid-base. Bronsted-Lowry acid-base is one of the most common types of acid-base. Arrhenius described bases that exist in water. So Arrhenius has a definition of acid-base, and it's anything that creates hydronium or creates hydroxide. Bronsted and Lowry say that an acid is a hydrogen ion donor. So we typically abbreviate a generic Bronsted-Lowry acid as HA. Well, we show it as HA, and we say that in a chemical reaction, it goes from HA to A minus. It's an election cycle, and I still have a Wisconsin phone number, so I get calls every single day from Wisconsin. It's crazy. Acid is hydrogen ion donor. HA can give up H plus and become A minus. Do you know what we call A minus? The name for A minus in this chemical reaction? Well, which one? Conjugate acid or conjugate base? If it has already given up its hydrogen, now it's a base, and it's a base that is related to the acid, so it's a conjugate base. Do you guys know what conjugate means? reciprocal or opposites. I don't mind that. What? Partner. Yeah. Opposite partner. I always think back to high school Spanish class. Conjugate verbs, right? Like to be, to run, huh?
It's like how do you explain it? Like a two-part system, two parts.
But maybe not even just two parts. You conjugate verbs, in Spanish you can conjugate verbs 100 different ways. So it's more like things that are different but related to each other. Not quite a synonym, because synonyms I think give the same meaning. But relatives, almost like resonance. And actually we say that systems that are in resonance are conjugated. Remember I said resonance is same, but different. Kind of like conjugate means like the same but different. So a resonance system is a conjugated system because they are related to each other. Conjugate base is the base form of the acid. The base is a hydrogen ion acceptor. So we typically show this as B reacts with H plus to give BH plus. And what do we call BH plus? Conjugate acid. It's the acid that is formed from a base doing its job. Do you guys agree? If something gives up a hydrogen, it could take it back. So after you give up a hydrogen, you become a base. If you've accepted a hydrogen, you could give it away. So after you've accepted a hydrogen, you become an acid.
That answer is exactly right.
Great. These are totally inverses of each other. In general chemistry, we often tell you an acid is something that has like H in the front of it, HNO3, H2SO4, except for acetic acid, CH3COOH, or C2H. I don't know how they abbreviate it. I don't like how they abbreviate it that way. And a base is something that has OH in it, which is why some of you guys yesterday looked at those molecules that had OH groups and said, that's a base, right? It's got hydroxide on it. That must be the polyatomic ion hydroxide. Throw it out the window. It's far too simple for this class. What we'll look for, obviously, yes, acids, actually pretty straightforward. You need to have a hydrogen in order to be considered an acid. But we do have things that are very weak acids and things that are very strong acids. So whether it has a hydrogen or not doesn't necessarily mean that it will give that hydrogen away. A base, on the other hand, has some criteria. In order to accept a hydrogen ion, it must donate electrons. The electrons that it will donate are either pi electrons, so it will donate electrons from a pi bond, or it will donate lone pair electrons, so it will donate electrons from a non-bonding region. Why would it donate pi bonds? Because MO theory says pi molecular orbitals are higher energy than sigma molecular orbitals. Higher energy means easier to get rid of, easier to do a reaction with. So pi electrons are higher energy. Not all lone pairs serve as good bases, though. For instance, we have talked about this compound, CCl4. This has no good lone pairs for being a base. Because those halogens all have 3 lone pairs, but those halogens are all bonded to a carbon, so they're kind of stuck there. They're not going to share their lone pairs very well. But something like chloride can be a base. Chloride has 4 lone pairs. It only has lone pairs, and it could share one of its lone pairs. So halogens bonded, not very common. Halogens not bonded, much more common. Okay, here, let's make it even more confusing. CH3OH, 2 lone pairs. Hardly any different than the halogens. The oxygen is bonded as much as it likes to be. It's got its normal amount of lone pairs, but oxygen can be a base. Isn't that fun? So I want you guys to look at these structures down here, and I want you to consider what could be an acid and what could be a base. After you consider that, we'll decide, is it good at being an acid or is it good at being a base? Because those aren't always the same thing. Just decide, can it be an acid? Can it be a base? And we'll go from there. Oh. Yeah, you're kind of looking at pairs, but it doesn't need to be acid-base pair. I don't know why they're paired up. Just for comparisons.
Can it be neither an acid or a base?
True. It can be neither.
Professor,
Yes.
what's the criteria for an acid? General criteria.
Has to have a hydrogen.
That's pretty much it.
Yeah. I mean, yeah.
Professor, is there a preference? Like, what if it has lone pairs and hydrogen?
Good. Then it can be both. What's available? Yeah. Did you just draw a lone pair on that carbon? Why?
It should be a hydrogen, shouldn't it?
Right.
Trying to fill its octet.
It should be a hydrogen because it has no charge given. And we can never assume formal charge. So if the charge is shown as neutral, then it's a hydrogen that's missing. Good.
If that's the case, then I think that can be dependent on what solution it's in. Like,
Whether it's good acid or a good base.
whether it dominates or accepts.
True. What is it in competition with, essentially?
Yeah.
Yep. A minus is conjugate base.
Conjugate base. And then HA is the acid?
HA is the acid.
Okay, HA is the acid.
So with assuming like lone pairs, that's only for carbon when there's no charge on the carbon. Because like for this amine group, there's like NH2,
So
right?
there's lone
But
pairs
there's nothing else shown on it.
So we know it has 2 bonds to the hydrogens, 1 bond to the carbon.
So it has a pair.
It has 1 pair.
And there's none of the pi
Get
bonds
rid
here.
of.
Yes.
Therefore, it's better base.
Better base than what?
Where it just
Can be a base.
can't be a base.
Yes. Yep. It has that lone pair, so it can be a base. It's just kind of this weird exception. It has lone pairs, but no one would call it a base. But this also has lone pairs, but it does have a base. So it's this odd thing about halogens. The halogens, if they're in a structure, the halogens are not bases. In fact, halogens are bad bases as halides because the hydrogen halides are such strong acids. HCl, strong acid. HBr, stronger acid. HI, one of the strongest acids. So this can be a base. It's not very good at it. But in the context of being bonded to a structure, it really wouldn't be a base. It's an odd exception. Yep, any halogen in a structure won't be considered a base. So let's talk about these first two. The structure on the left. Acid, base, neither, both.
Depends on its circumstance.
Depends. Can it be an acid? Does it have hydrogens to donate? Yeah, it's got lots of hydrogens to donate. So could be an acid. Does it have any lone pairs or a pi bond? No. Did any of the structures I have give you a pi bond? I don't know what I was thinking. We'll look at some others on the next page that do have pi bonds. We'll see them being bases. CF3. Won't be either. It's got lone pairs, but again, it falls into that weird exception where those halogens lone pairs will not be shared. So this is neither. How about this 2-carbon chain with NH2? Can be a base because it has lone pairs. Can be an acid because it has hydrogens. It has hydrogens in different places. It has hydrogens attached to carbon, and it has hydrogens attached to nitrogen. Any intuition about which hydrogens are likely more acidic? The nitrogens. We'll talk about how we can figure that out. And the next one, again, it could be both. Because if we're saying this could be an acid, then technically this could be an acid as well. But it definitely could be a base from that lone pair. On the last two, I guess technically both, right? Because again, they both have lone pairs. And although oxygen would be a better acid, we can't say for certain that the carbons can't be acids. They have hydrogens to donate, so they meet that criteria.
So certain components of a compound could be a better acid? Or
Correct. Certain hydrogens might be more likely to be donated.
So are you saying the hydrogens coming off of all of, like the assumed hydrogens coming off of all of the carbons are eligible?
They fit the criteria. They are hydrogens, so they could, in theory, be donated by that carbon.
But they might not be.
Correct. They might not be, but they could be.
Would that just require the whole compound to be dissociated?
No, because actually, to be a hydrogen ion donor doesn't mean you have to dissociate the bond. We're going to look on the next page at how this is one view of hydrogen ion donation. But if there's a base that is already there willing to take the electrons, then it's likely to just exchange it, donate and accept at the same time.
Within the same compound?
It could be within the same compound, sure. But a lot of times it's intermolecular. If I wanted to take these two half equations, the equation of acid, the equation of base, and combine them, I think you guys would agree that H plus cancels out from the left and the right. And I could say HA plus B forms A minus plus BH plus. And I'm still showing a hydrogen ion and a hydrogen acceptor without saying particularly that H plus is floating around within that. Now, pKa is a way that we often talk about Bronsted-Lowry acids and bases. pKa is opposite the log of the acid dissociation constant, which is the chemical equation concentration of A, concentration of B, or A minus. I'm going to start that sentence over. Concentration of H plus, concentration of A minus divided by the concentration of HA. That is the dissociation constant. It says in a sample how much of it remains intact as the acid, how much of it remains dissociated as the donated ion, and the conjugate base. Typically, the number on top is very small compared to the number on bottom, which means that we get a decimal here. We get a number less than 1. And since log says, what value do I raise 10 to get that number, I would need to raise 10 to a negative exponent to get a number less than 1. So we typically take opposite the log. This is what the p means. P means opposite the log. And we report these instead as positive numbers. A more positive pKa, actually, I'm not even going to say larger pKa. I'm going to say more positive pKa. No, because if pKa is opposite the log, the smaller this number is on top, meaning the worse the acid is, then the more positive the pKa becomes. If this number on top ever gets so large that dividing it by HA leaves me with a number greater than 1, then actually greater than 10, then negative the log becomes a negative number. A more positive pKa is a better acid. And a more negative pKa is a worse acid, or another way, oh, I'm sorry. Oh, can you erase it? Hope you didn't write that in pen. Yeah, I screwed up. More positive pKa is worse acid.
I was going to say exist.
Yeah, the words are coming out of my mouth all wrong. Or another way we can look at that is this acid has a stronger conjugate base. If its conjugate base exists, then that conjugate base will rip hydrogens away from anything and never give it back. Something with a more negative pKa is a better acid, but a weak conjugate base. Something with a more negative pKa gives away its hydrogens readily and never wants them back. So when we look back up here and we said, oh, all these different things could be acids, could be bases, we can now look at those different acids and say, are they good acids or are they bad acids? First, with just this hydrocarbon, the pKa is in the 50s to 60s, which is about as high as it can get. That's about as positive as it goes. So this is a terrible acid. It is not good at giving away its hydrogens. Does it have hydrogens to give away? Yes. Will it? No.
Could we have guessed that?
Probably.
The fact that the hydrogens are all bonded with carbons?
Correct. You could have guessed that. Intuition told you that already.
Yeah.
But it stands to reason it could still
Right.
give it away. Here, we have pKa of 50 to 60 on these carbons. On the nitrogen, we have pKa in the 30s.
So it's usually like a better base than it is a better acid. Would that be
If it's not a better base, then it's a better acid. If it's not a better acid, then it's a better base. Is that what you're saying?
Well, for this example particularly, with its pK being in the 30s, it's a better base than it would be an acid.
Yes. It is actually it's a very good base. We'll talk about better bases, though, in a little bit. For right now, we'll focus on the acids, and we'll say the nitrogen is a better acid than the carbon. So if we were to compare when nitrogen can donate electrons donate hydrogens versus only carbon donating electrons, this compound, the nitrogens are better acid than the CH groups. NH will donate its electrons better. It has a more negative pKa relative to the CH.
But it's still not a very good acid.
Not a very good acid. But it can, again, donate its hydrogens, and it would donate it, the nitrogen would donate its hydrogens before carbon would. Same thing here. The pKa of OH is in the 15 to 18 range. Orders of magnitude better than the nitrogen and far better than something that only has CH. Delaney.
How do you know what the pKa's are?
I'm telling you.
Oh, okay.
I will never ask you to guess a pKa. Some organic chemistry professors give a table of pKa's on their exams. I don't think you need it. I don't think it helps as much. What we're going to actually do is talk about a system that helps us compare acids and bases. First, I want us to flip onto the back side where we consider a few chemical reactions. First, we see the chemical reaction of just benzoic acid, where it dissociates its OH bond and forms O- and H+. We say that the pKa of benzoic acid is about 5. So we can see that the OH of benzoic acid is even more acidic than the OH of something on a different compound. Not all OHs have the same pKa.
I was going to ask, is that because of the way that the structure is, the electronegativity is?
It has a lot to do with the resonance, actually. If we look at the next reaction, where we show benzoic acid with hydroxide, we now have two acids to consider. An acid on the left and an acid on the right. This is a true equilibrium reaction. This is what you guys are doing in lab this week, using sodium hydroxide to deprotonate benzoic acid. Did you shake your head? Oh, okay. We know that the pKa of benzoic acid is about 5. The pKa of water, you know, water is not so different from this alcohol compound. Really, the only difference is there's a bond to carbon instead of another bond to H. The pKa of water is about 15.6. Which of these acids is a better acid? Benzoic acid, because it has a more negative pKa, which means that it is going to do its job better than water. So this little equilibrium that we have, it actually looks more like this. For all of the reactions that go forward and deprotonate, you guys heard that term before, protonate and deprotonate. You know why we call it that? The hydrogen ion is a proton, nothing else. There's no electron, there's no neutron. When we deprotonate benzoic acid, we do that favorably. It's favored in reaction. The water is not as good. So we say that this side of the products is favored by equilibrium. Gavin.
In Chem 2, our acids always had negative exponents, and then anything that was greater than like times 10 to the negative 2 was considered like a negligible acid, but these are all like large positive numbers.
You might have been looking at Kas and not pKas. Ka would be taking this number like 50 and saying 10 to the negative 50 is the Ka. That's a negligible acid. Whereas this, 10 to the negative 5, it is actually a weak acid. We're going to look at the next one, where benzoic acid is shown in equilibrium with water to deprotonate benzoic acid and form hydronium. The pKa of hydronium, H3O+, any guesses? Around the same. Interesting. Do you mean same around 5 or same around 15.6? Oh, okay, good. No, it's actually -3. So 10 to the -3 is 10 to the 3, and that's a substantial acid. I think that's what you're getting at, Gavin. This has a Ka of 10 to the 3. It has a pKa of -3 to compare. This has a Ka of 10 to the -5, Ka of 10 to the 3. The pKa is opposite the log of those.
Yeah, when we did it, like pKa was always for stuff that only partially dissociated and was weak, and then Ka was for like strong.
We're going to use pKa's all semester, whether it's strong or weak. Saray.
So when you were talking about pKa, are you usually talking about the molecule overall, or just certain sections? And how do we differentiate?
Good question, actually. Yeah, pKa is relative to a bond. Citric acid is a cool example of a molecule that has a lot of different Kas. I think I drew it wrong. No, here it is. Citric acid has these 3 groups that all look quite similar, but they actually all have different pKas. They have different Kas. Maybe we can come back to that one later, but when we talk about pKa, we are talking about a specific bond or in a molecule. But we can say bonds in general, like CH, 50s to 60s. We can give these ranges for bond types. Which side of the equilibrium is favored? Hydronium is a better acid than benzoic acid. So if hydronium exists, no, it doesn't. It deprotonates itself, and it protonates benzoic acid. This side is favored by equilibrium. Now, we've been talking about electron arrows and how we can use electron arrows to show how electrons move. We're going to do the same thing here. On this top reaction, how could I show an electron arrow on the left to describe how the bond breaks to the right? What could I show?
Arrows moving from the hydrogen back to the oxygen.
I don't want to start at the hydrogen. I'm glad you brought that up, because the hydrogen is a nucleus, and there are no electrons there. I want my electron arrow to start at an electron source.
From the bond to the oxygen?
From the bond to the oxygen. Do you remember we said earlier? It's gone. Bonds break toward the more electronegative atom. These electrons, they break toward the oxygen, away from the hydrogen, leaving it as H+, giving the oxygen another lone pair. Do you guys see this resonance system? 1, 2, 3. A 3-atom system with a negative charge and a pi bond. We're going to talk more about resonance in a second, too. What could I show here? What arrows could I use in this second reaction to show not only the bond breaking between O and H, but a bond breaking between hydroxide and H? Did I say breaking? A bond breaking and a bond forming in this step.
So you could do the same thing with that bond between oxygen and hydrogen, and then the lone pair on the hydroxide, you could drop directly towards the hydrogen.
Perfect. Same thing with the OH bond breaking. It breaks towards the oxygen and benzoic acid. But now a lone pair on hydroxide is being used to bond to H. We can draw in the lone pairs, or that negative charge informs us about a lone pair, so we can actually start from that negative charge. What we're trying to communicate is that for this acid-base reaction to occur, benzoic acid and hydroxide have to run into each other. And they have to run in such a way that hydroxide shares its electrons and OH takes electrons back to O. Two arrows, one that shows a bond forming, one that shows a bond breaking. What do I do in the last one?
Same thing, except the lone pair would be from the H2O.
Same thing. But this time I don't have a negative charge on water, so I must show the lone pair. I can't start my arrow at O. Why? Because O is a nucleus. O is not electrons. The lone pair on oxygen is attacking that hydrogen, being donated to that hydrogen, and then the OH bond breaks. Fun, right? And did you notice how my arrows can really do whatever I want? I can take this, this arrow in this last reaction. As long as it starts and it ends in the right place, it really doesn't matter what it looks like. I think some of the fun ones are when your arrows are in kind of tight places, so you end up having to go around molecules in order to come back. It doesn't matter because we're drawing a chemical reaction that is happening in three-dimensional space on a flat piece of paper. So it doesn't matter where our arrow starts and goes to. Well, it matters where it starts and where it ends. It doesn't matter where it goes in between. So unlike with resonance, these electron arrows are happening between reactants. Resonance forms don't exist. We're just showing different perspectives of one molecule. But here, we're showing two molecules running into each other. We're describing what needs to happen for that to occur.
How do you differentiate between the arrows? Like, is there ever a scenario where there's arrows that explain resonance forms and arrows that explain?
No, these are all curved arrows.
Okay.
And we say they're curved arrows because they're not straight arrows. Here's a reaction arrow. Here's a resonance arrow, equilibrium arrow, resonance. Those are straight arrows. Curved arrows are used for electrons.
Oh, so the arrows that are in between the two are what tell you whether or not it's resonance.
Yes.
Not the curved arrow.
Yes, this tells you it's equilibrium or a reaction
Gotcha.
and not resonance. But curved arrows are just for electrons. We're not going to get into this until a little bit later, but we can actually differentiate between one electron moving and two electrons moving using our curved arrows. You see the difference here? One electron has one stick at the arrowhead. Two electrons has two sticks at the arrowhead. Okay, so how do we differentiate what's a good acid and what's a good base? How can we make predictions about what has a higher pKa, what has a lower pKa? This is what we have underneath where we talk about karyo. The first thing that impacts the strength of an acid or a base is charge. A more positive charge is more acidic. A more negative charge is more basic. So in those first three structures, and I know that they printed a little blurry, I want you to label which structure is the best acid and which structure is the best base. Actually, I want you to do the same thing in the next set of three compounds. Label the best acid, label the best base. And we're not going to have a lot of time to stick around on these because we've got more to do. So for the first three, what is the best acid? The one on the far right with a positive charge. What's the best base? far left. Does that change with the next 3 compounds? Best acid has the positive charge. Best base has the negative charge. Straightforward, right? Okay, here's a weird thing for you. There's always exceptions. And this isn't an exception that has a rule. I just want you to know this is not a hard, fast rule. There's so many factors here. What we have here is an amino acid. And amino acids will show us that, well, I guess actually what I wanted to show you was if you have a protonated OH on that amino acid and you introduce this to a base, you get what I've shown on that sheet. Although the nitrogen is more positive and the O is neutral, it's the OH that acts as the acid, not the NH3+. So what I like to say is this is true if all else is the same. But here, not everything is the same. Yes, nitrogen is positive. It's more positive. It should be more acidic. But these are different atoms that are at play. So because not everything is the same, charge doesn't really apply. Here's our next one, atom. There's 2 things to consider. If you're comparing 2 acids that are in the same row, more electronegative is more acidic. But if those 2 atoms are in the same family, if they're in the same group, a larger size is more acidic. You guys remember that electronegativity climbs up a family. So in a family, it does not follow electronegativity. It follows size of the atom. This has to do with polarizability. If I have HF and HI, HF forms F minus, whereas HI forms I minus. And I minus is much bigger, which means that it can distribute that charge over a much larger area. In fact, it can even polarize its charge so that it hardly even knows it has a charge. It's better at being an acid because it's more stable holding the negative charge as a base. It's a better acid because it's a worse conjugate base. On that next row, there's an SH, OH, NH2, CH3. Can we rank those by acidity? What is the most acidic? What is the least acidic?
Even though it's not more electronegative,
Correct.
but because its size is larger,
Correct.
it is more acidic.
HI is more acidic because of its size and not because of its electronegativity. Yep. HF is actually not a very good acid compared to HI. Our most acidic? HS. It's in the same family as OH, but SH is bigger. OH, NH, and CH3 are all in the same row. And oxygen is the most electronegative. So oxygen being the most electronegative, but sulfur being bigger than it, we know that oxygen is more acidic than the other 2, and that sulfur is more acidic than oxygen. So our ranking goes most acidic to least acidic. All right. Rule number 3 is resonance. And sorry, this is not rules. These are trends. which is why we can't really put them all together. Remember here we said more positive, more acidic, more basic, more negative, and that was not true here. The more positive thing wasn't more acidic. The neutral thing was more acidic. That's because they weren't the same atom type. So all else wasn't equal when we compared charge there.
Would phosphate be more acidic than oxygen? Even on the same realm?
I think
Phosphate's more.
pH and OH might have similar acidities because pH is both back 1 in terms of electronegativity, but down 1 in terms of size. But I don't see pH very often. When you say phosphate, you're maybe thinking of phosphoric acid, which actually has OH. But I don't see pH very often, to be honest. Then the R stands for resonance. Increased resonance means increased stability. Now this one is such a challenge because you can't predict acidity or basicity without looking at the conjugate. So increased resonance in the conjugate base means increased acidity in the acid. Resonance is a stabilizing force because those negative charges, those positive charges, they're not just on one atom, they're delocalized across a system. So resonance stabilizes, and if my acid has a lot of resonance in the conjugate base, then my base is quite stable. And my acid, as a result, is more acidic. If I have increased resonance in my conjugate acid, I forgot my E in base, then I have increased basicity in my base. Resonance stabilizes what you have so you can predict what came before it better. To determine whether something is a better acid or base, you look at the resonance. So let's look at these next 3 compounds, which have varying levels of acidity. The first one gives away the most acidic hydrogen from the oxygen. Based on atom, oxygen is more acidic. No resonance in that conjugate base, not a good acid. The next structure gives away hydrogen from the OH. And this actually has resonance. I have that 3-atom system where oxygen can donate a lone pair and put a negative charge into the ring, which actually creates a new 3-atom system inside the ring, and then another 3-atom system inside the ring. This conjugate base has a total of 4 resonance forms. Compared to 0, that's a much better acid because it's a more stable conjugate base. Our last one, as a conjugate base, has a negative charge on O, 3-atom system, charge, and a pi bond. This only has 2 resonance forms, but in both resonance forms, the negative charge is held by by an electronegative atom. The negative charge is held by oxygen. In these resonance forms, there are 3 resonance forms where carbon holds a negative charge. Carbon does not hold a negative charge very well. So resonance has a contributing effect from atoms. It's not just how many more resonance forms, but it's what atoms are holding the charge in those resonance forms. These go from worst acid to best acid. This had a pKa around 16. This has a pKa around 10. This had a pKa around 5.
So the more resonant structures there are possible, the better acid tends to be.
Typically, unless it has more resonance forms, but with less contribution. These two are 50-50 equal resonance forms. But these are like 90%, 10%.
So that third one doesn't really have a major contributor, it's 50-50.
Correct.
Whereas that middle one has a major contributor and minor contributors.
So having minor contributors is better than having no contributors, but having multiple major contributors is better than having more minor contributors.
What's a contributor?
We had those 3 rules: minimize charge, maximize octets, appropriate formal charge.
It's like the most viable resonance structure, right?
The one that follows those 3 rules the best is a major contributor. It's what we're saying, the Lewis structures don't exist. The formal charges, I'm sorry, the resonance forms don't exist. But
So, and lesser contributor, you said it's a weaker acid? Is that what you said?
one more time.
You said the minor contributor is a weaker acid?
No, what I meant was having fewer but major resonance forms is better than having more minor resonance forms. It's confusing. Here's the deal. I'm not giving you guys trick questions. This one's tricky because I'm saying increased resonance increases stability, but the one that has the most resonance isn't the most acidic. And that's because there's these compounding effects. I will give you these questions that have straightforward trends. Follow the trends as described. But I want you to be aware of it.
So just overall, having major contributors in a resonance structure is more important than having a sheer number of resonance forms.
Correct. Having more major forms is better than just having more forms. Induction is our I. Rowan?
So in that one, it was like, it had more contributors to resonance, and it also had the negative on like the electronegative atom. If it had like one, and then the other had like the other, is one of those preferred?
Well, this one has... No, I don't think I understand.
Like, that one has the negative charges on oxygen.
Yeah.
Which is preferred.
Yep.
If the other one had the negative charges on oxygen, but like,
Still had 4 resonance forms, and all 4 of them were on oxygens? Yes. So if all things are the same, more resonance, more acidic, or more stable. Yeah.
Because those would all be major forms.
They'd all be major. Okay, induction is a push and pull of electrons. Things that are not very electronegative, they push their electrons towards that electronegative acidic atom. Makes that oxygen a good base. But if that oxygen is near things that are very electronegative, electronegative things pull electron density towards them, away from the oxygen, making it a better acid. Induction is forcing something, forcing electrons in or forcing electrons out. If I force electrons in, it's more likely to donate electrons. If I force electrons out, it's more likely to accept electrons. It's more likely to donate its hydrogen.
Remember we talked about in and out of like particular atoms?
Just in and out of the molecule, in and out of this region. Carbon, not very electronegative, so its electrons get pushed towards the electronegative oxygen. Fluorine, very electronegative, so electrons get pulled away from the electronegative oxygen. Thank you, Sammy. All right, the last one is how the orbital comes into effect. More S character is more acidic. less S character is less acidic, but we can flip this, and if we're talking about lone pairs, SP is less basic, a less basic lone pair, and SP3 is more basic lone pair. So we have two different sets of structures, one that compares carbons, one that compares nitrogens. For the carbons, I want to compare acidity. On the far right side, the sp carbon is the most acidic. But on that right-hand molecule, the far right side, the sp nitrogen is the least basic. So we can use the orbital type to determine the acidity in our structures. sp3 is the least acidic. sp is the most acidic. Most acidic, least acidic. It flips when we start talking about the lone pairs on these nitrogens. That lone pair is the least basic if it's sp, and that lone pair is the most basic if it's sp3. Wow, that was a lot. Sorry. And just 8 minutes left to cover the next topic. Luckily, this next topic has a lot to do with arrow pushing, and you have already seen arrow pushing in play with resonance and with the Bronsted-Lowry acid-base stuff. So this last part should be easy enough to get through. Unfortunately, everybody wants to call their stuff acid-base. Lewis also defined acids and bases. But he got to the game late, so we often refer to his differently. A Lewis acid is an electron pair acceptor. We call this an electrophile. I like to abbreviate it as E+. A Lewis base is an electron pair donor. We call this a nucleophile because it bonds to a nucleus, and I like to call this nuc minus. All Bronsted-Lowry acid bases are Lewis acid bases because to donate or accept a hydrogen ion, you need to accept or donate an electron pair. All Bronsted-Lowry acid bases are Lewis acid bases, but not all Lewis acid bases need to involve the exchange of a hydrogen ion. Squares and rectangles again. So on your worksheet, I want you to notice the top two reactions under Lewis acid bases. Those are Bronsted-Lowry reactions. That's just acid-base donation. I'm sorry, hydrogen ion accepting and donation. But I want you to label what's the nucleophile and what's the electrophile. On the top reaction, what is my Bronsted-Lowry acid? What's my Bronsted-Lowry base? Hydrogen ion acceptor, hydrogen ion donor. So base, acid, nucleophile, electrophile. All Lewis acids are Bronsted-Lowry acids. All Lewis bases are Bronsted-Lowry bases. Do you remember I said that a carbon can be an acid? This is what we see next. We see a carbon that is next to a positively charged carbon, and we see that carbon donating an electron. Donating a hydrogen. Base, nucleophile, acid, electrophile. Now, what I want you to do on the bottom half is I want you to both label as nucleophile and electrophile. I want you to recognize that not all of them are Bronsted-Lowry anymore. Some of the last 5 reactions down there are just Lewis acid-base. They don't involve the exchange of a hydrogen ion. They show bonds forming or they show bonds breaking. And I want you to get practice with your arrow pushing. So for the ones on the left and the bottom, I want you to be able to add arrows to make the change that you see. The 2 on the right, I want you to draw the change based on the arrows shown. I'm going to go through one of them with you guys. Let's look at that top structure, 6-membered ring with a double bond next to HBr. And we're seeing a positive charge form on the carbon and a negative charge form on the bromine. If we spot the difference, the HBr bond needs to break. Which way does that HBr bond break? Towards the more electronegative atom, towards the bromine. That's one of our arrows. Starts at the electrons, moves to the bromine.
It's not shown, but would that hydrogen then be pushed towards the
Well, we're not done yet. But remember, curved arrows don't show atoms moving. Curved arrows show electrons. So I go from CH and CH to CH and CH2. This carbon has bonded to a hydrogen that it wasn't bonded to before. And the carbon-carbon pi bond has broken. So the carbon-carbon pi bond, base. The pi bond is acting as a base here. There is no way for me to use an arrow that shows which carbon is using it. And that's fine, because we know the change, and so we know which one used them. But if you'd like to, you could show an arrow like this, where it kind of goes through that carbon to show that that carbon is the one using it. Now let me show you one on the right-hand side. You know what? I'm going to do the one on the bottom because I think it didn't show up very well. It should show an arrow starting from the oxygen and ending at the boron, but you can't really tell that there's an arrow head pointing at the boron. Both neutral, but oxygen is forming a bond to boron, and that's it. No other bonds are being described as being broken. BH, all stay there. Carbon to oxygen, all stay there. Please do not hallucinate arrows. This is one of the most common things when students try to interpret arrows with Lewis acids and bases. They're confused because they don't know why it should show up the way that it looks weird to them. So they invent arrows. I've had students take my exams and add arrows onto the questions so that their answer makes more sense. Not what I'm looking for. Interpret what you're being shown. What's wrong with the product? The charges aren't shown. There are charges. What charges are missing? Where? When boron has 4 bonds, it takes on a negative charge. I can't go from net neutral to net negative, though. I can only go from net neutral to net neutral. Look at how I went from net neutral to net neutral. Everything was negative. Everything was neutral, and then I had a negative and positive.
So there's a positive charge in the oxygen?
That's a 3-bonded oxygen. That's a positively charged O. Net neutral. You can create charge. You can get rid of charge. Look at the very bottom reaction where you start net neutral and you end net neutral. You can destroy charge by combining those charged species. Okay, if you have the time, I'll put the rest of the answers on the board. I've already taken more of your time, so thank you for that. I'll keep the recording going, so if you need to leave, you can catch this on the recording. But you have some practice problems to do with this to help make it make sense. I'm really running out of space, though. Okay, thank you guys for your time. Have a good day. Have a good weekend. Unit test this weekend. I'll send a message about what to expect for it.